Hello, y'all. Welcome to lesson 52, structure 2.2.14. This is an HL topic of my DP chemistry curriculum. We're talking about formal charge values, how they can be calculated for each atom in a species and used to determine which of several Lewis formulas is preferred. We'll be able to apply formal charge to determine a preferred Lewis formula from different Lewis formulas for a species. So when we start talking about formal charge, we should consider the Lewis structures of some atoms or molecules. So let's start with CO2. You should be able to draw CO2 currently, and your drawing should look something similar to this: a linear atom, two double bonds to each oxygen, or a linear molecule, two double bonds to each oxygen with some electron pairs. But following our rules for Lewis diagrams, I could theoretically draw oxygen as such. There's no rules telling me how many bonds I can or can't make as long as we follow the octet rule. And you'll notice 2, 4, 6, 8 around the oxygen, 2, 4, 6, 8 around this oxygen, and finally 2, 4, 6, 8 around the carbon. So both of these diagrams are possible. These are both possible Lewis diagrams. But we know that the one on the left is correct. But why? Why is this the possible correct diagram? What actually tells us that? Well, this is why we have formal charge. So formal charge basically allows us to pretty much identify the more likely structure. Because you can often draw multiple Lewis structures, but this one tells us what is correct. Now, what is formal charge actually for a real definition? Formal charge is the theoretical charge of a molecule or of an atom on a molecule, of an atom in a molecule based on electron distribution, which sounds very similar to our charges of atoms or oxidation states, but formal charge is a little bit different because it does something else. It's more just comparing valence electrons, compare our valence electrons of an atom with electrons that belong to it after bonding, which again doesn't make too much sense until we start counting these. Um, because we're basically just counting which electrons belong to atoms. And the rule of thumb for formal charge is the closer to zero, I'll write that one out, the closer to zero all values are, the more stable the configuration. Okay, so we have some ideas about formal charge, but we need to actually learn how to calculate it and apply it. And this will help us understand it a little bit more. So before we go into calculating it, we need to know the formula. So the formula for formal charge. And I'm going to just start doing FC to represent formal charge. So formal charge is equal to the valence electrons minus the sum of the bonds plus lone electrons. So this is bonds, and this is lone unbonded electrons. All right, so now we have a formula, and we have some ideas of what the heck formal charge even means, but let's put it into practice to actually solidify our ideas. So let's look at our two CO2 diagrams again. C double bond O, and we have to look at the formal charge for each individual atom here. Now, The first oxygen has a formal charge equal to its original valence electrons, which is 6. So VE is original valence electrons. So there are 6 valence electrons in a standard oxygen atom, minus the number of bonds. It has 2 bonds. A double bond is 2 bonds, plus the number of lone electrons. That's 2 and 4, a total of 4 lone electrons. So this has a formal charge of 0. This also applies to that oxygen right over there because, again, it's 2 bonds and 4 electrons. So these both have a charge of 0 and 0. All right. The carbon, let's do the carbon in a different color, has a formal charge. It normally has 4 valence electrons minus. It has 4 bonds and 0 lone electrons around it for a sum of 0. All right, so the formal charges for all 3 atoms in our carbon dioxide as drawn is 0, 0, and 0. Well, we know that the closer to 0, the more stable the configuration. So this must be right, but for science sake, let's compare it to our other configuration. Oxygen triple bonded to carbon, single bond to oxygen. I knew it drew it backwards from the previous way, but it doesn't matter too much. All right, this oxygen has a formal charge of, again, 6 valence electrons, minus. It has 3 bonds and 2 unpaired electrons for a total formal charge of 1. This has a charge of positive 1. The formal charge of the other oxygen is a little different. It's 6 minus 1 bond plus 6 electrons for a formal charge of negative 1. Carbon, turns out, is still the same equation. So carbon's still 0. So now we can see that between our left and our right carbon dioxides, the oxygens are quite unstable, having more than 0 overall charge, while the left ones are perfectly stable all across the molecule. This tells us that this is the correct configuration. So this is what formal charge allows us to do. Let's take another example to kind of understand why some atoms do not have an expanded octet, but instead are electron deficient. So let's look at the example of boron trifluoride. There are 2 possible configurations. One that we've been using, which we may learn today is incorrect, and one that allows boron to have a full octet. So you'll notice that we do have quite a lot of the same element and same configuration, and we don't have to do formal charges for all of them. So we'll go ahead and I want you to pause the video, try it yourself, and then come back. I'm going to start going over the answers now. So the formal charge for our fluorines with 1 bond, those are going to be 7 valence electrons minus 1 bond plus 6 electrons for a total of 0. So that's 0, 0, 0, 0, 0. Our formal charge for our boron with all single bonds is going to be 3 minus 3 bonds plus 0 extra electrons for a formal charge of 0. Our formal charge for fluorine with a double bond is going to be 7 minus 2 bonds plus 4 electrons for a formal charge of 1. Oops, I realize I made a mistake here. 1. And that's a plus 1. And our formal charge for boron with a double bond is 3 minus 4 plus 0, which is negative 1. So now we can understand why some atoms actually do not have a complete octet. Boron trifluoride is more stable having 6 electrons than having 8, according to formal charge. This is why we draw the structure this way. On the same vein, let's do one more example before we finish up the topic. Let's do sulfate, SO4 2-. You can give it a shot and try and draw it yourself, but we're looking for a configuration with very low formal charges. So one of two possible ways is sulfur with 4 oxygens around it. Now the whole molecule is going to have a 2- charge. Another possible configuration is sulfur has an expanded octet. And so we give 2 of these oxygens double bonds, providing 6 electron domains, or what would have been possible for 6 electron domains, but still 4. And we have this configuration on the right. So go ahead and try and identify formal charges, pause the video, and come back to it now. So formal charge for oxygen with a single bond is going to be 6 minus 1 bond plus 6 electrons for a total of positive 1. Or sorry, I did that math wrong. That is negative 1. So negative 1, negative 1, negative 1, negative 1, negative 1, negative 1. Our formal charge for sulfur with only single bonds is going to be 6 minus 4 bonds plus 0 for a total of 2. All right, so now we can go to formal charge of oxygen with a double bond. That's going to be 6 minus 2 plus 4 equals 0. So these 2 oxygens have a formal charge of 0. And finally, formal charge of sulfur with the double bonds is going to be 6 minus 6 plus 0, which again is 0. So we can see that when we draw sulfate, we should be drawing it with an expanded octet because it is no longer having 8 electrons, but instead is more stable in this configuration where it has 12 electrons. So this is the more stable. All right, so the last part of formal charge is more of a limitation. So one of the limitations of formal charge, and the main one, is that it doesn't account for electronegativity of atoms. So what do I mean by that? Well, when we look at nitrogen dioxide or dinitrogen monoxide, N2O, we could draw it in a couple ways. We could draw it such that we have a triple bond to another nitrogen, single bond to oxygen. We could also draw it where it has a double bond to a nitrogen, double bond to an oxygen. Both are acceptable. They follow the general rules of Lewis diagrams. But when we calculate formal charge, we get a 0, a minus 1, or sorry, a 0, a plus 1, and a minus 1. While on the other side, we get a minus 1, plus 1, and 0. So how do we know which is right? Because formal charge doesn't tell us how to differentiate between these two. It says both should be correct. So we have to account for electronegativity. Now, electronegativity, we may remember, is the tendency to attract shared pairs of electrons, meaning that also what we learned is more electronegative is more partially negative. So we're trying to think about things that are more negative. So in this example, which is more electronegative? And the answer is oxygen is more electronegative. Therefore, it should be more partially negative, meaning that we want to take the structure that provides a negative charge to the more electronegative element. So the more electronegative element should have the negative formal charge. So that is basically all there is to formal charge. I hope this helps and have a great day.